Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 17, Design with Multiplexers, for the course Digital Logic Design for Chapter 4, Design with Standard Modules. The next slide is a disclaimer for you to read. There are many references in Digital Logic Design. I cite 3 of them here. In this lecture, we will talk about design with multiplexers, and this is very interesting lecture after we covered multiplexers and demultiplexers in the previous lecture, and we talked also about multiplexer expansion. Design with multiplexers. An important application of multiplexers is the implementation of combinational logic functions and networks. Any Boolean function, any switching function, set of functions, very complicated functions could be implemented with multiplexers as modular devices. Any k-variable function can be implemented with 2 to the power k to 1 multiplexer with no added logic gates. So if we have 4 variable function, and if we use 16 to 1 multiplexer, which is 2 to the power 4 to 1 multiplexer, we don't need any logic gates. We will not need any logic gates and could be implemented immediately. The data line at that time will be either zeros or ones. We will talk about it very shortly, an example. As you remember, the function of a multiplexer is defined by M0, D0, M1, D1, M2, D2, and so on and so forth. Well, M0 is the midterm of the select lines. So if we have 2 select lines, M0 will be S1 prime, S0 prime. M1 will be S1 prime, S0, and so on and so forth. So this is the general equation of a multiplexer for any function f. So based on this, we can implement any function with k variable by using a multiplexer 2 to the power k to 1. How we do that? Let's take an example. If we take a 4 variable function, this variable function can be implemented by 2 to the power 4, which is 16 to 1 multiplexer with no logic gates, such that all 4 variables are used as select inputs to the 6 to the 1 multiplexer. So if we use this select input, so we have the most significant bit S3, we have A, B, C, and D, S0, S1, S2, and 3. And we have the data line and F the output line. So how we implement this? Let's assume the function given to us as a function of a, b, c, d equals the sum of the midterm 0, 1, 2, 6, 7, 8, 9, 11, 12, 13, 1, 4, 5. So we can have 2 methods to do that, okay? To obtain the answer, this is really the answer for our problem. But how to obtain the answer, we have 2 methods. The first method is using express the given function as a sum of 3. Do apologize, it's not the right slide. Express the given function as a sum of we will express the given function as a sum of 4 variables, okay? And we will expand on it. Once we have it as a sum of 4 variables, we will expand on it. So what we have, when you say it is here M0, it will be A prime, B prime, C prime, D prime. What line is going to be selected? It will be D0. So we'll have M0, D0. How much the value of D0? Since M0 is there, D0 will be 1. D0 will be 1. Now, when we have 0, 0, 0, 1, I'm selecting D1. Do I have 0, 0, 0, 1? I do have the minterm 1, which is S3 prime, S2 prime, S1 prime, S0. Since it is there and 1, it is M0, M1. So D1 has to be 1. So M0, M1, D1, D1 will be 1. The same thing with 2. 2 is there. 2 will be 0, 0, 1, 0. Or S3 prime, S2 prime, S1, S0 prime. Since it is there, so D2 will be also 1. How about M3? M3 is not there. And the reason it's not there because when you write it down, it is 0 and the minterm value, which is M3. Since M3 is not there, since it is 0, it's not showing up. So D3 is 0. The same thing with 4 and 5. 4 and 5 also, 4 and 5 also will be zeros. So we have 3, 4, and 5 because the minterms are zeros, so the data line will be zeros. 6, 7, 8, 9 are there and all of them ones. Then after we have 10 is 0. CD10 is 0. Then 11, 12, 13, 14, and 15, all of them ones. And you see them ones because the minterms are there. So this is based on this equation, which explains the definition of a multiplexer. We have M0, D0. So if I have M0, D0 is 1. If I have M1, D1 is 1. If I don't have M0 in the function, so if M0 does not show up, the minterm is not there. So if the minterm is not there, what we have, D0 will be 0. D0 will be 0. And so on and so forth. So we obtain the answer based on the comparison between the general equation. Incidentally, we can say f of a, b, c, d, or we can say f of S3, S2, S1, and 0 because the same. A is taken to S3, B is fed to S2, C is fed to S1, and D to S0. So the sum of M0, 1, 2, 6, 7, 8, 9. This is the hardware implementation by using 16-to-1 multiplexer. And the beauty here, we did not use any gates. So for 4-variable map, we use 2 to the power 4 to 1 multiplexer. We need no gates. And this is the general rule. Now, let's repeat the problem with more complicated case. Here we are using a 4-variable function. We would like to implement a 4-variable function, but we are using 8-to-1 multiplexer. So there are two methods. We can express the given function as a sum of 3 variable minterms for the select line, because in the 8-to-1 multiplexer we have 3 select lines, S2, S1, and 0. So we'll express the function as a function of minterms, but the minterms for the 3 variables for the select line. And we will find the data values D0, D1 to D7. In method 2, we'll use a 4-variable K-map to calculate the data signal D0, D1 to D7. Okay? Both of them are easy. We need just a bit attention. Now in method 1, we have the function given to us. This is the same example we used it before. Is the minterm 0, 1, 2. Okay, we will open those minterms. Will be A prime, B prime, C prime, D prime. We will open them. Now we will arrange them as a function of 3 variable minterms. Namely, we'll have A prime, B prime, C prime. Now, if we take A prime, B prime, C prime, appears here and appears here, what you will get? Factor it out, you will have D prime or D, which is 1 according to Boolean algebra. The same thing we do with A prime, B prime, C. If we take A prime, B prime, C, A prime, B prime, C appears here only, and the coefficient is D prime. So with this will give me D0 when it is D1, D prime, or D, it is 1, so D0 is 1, and this will give me D1 is D prime. D1 is, so this will be D1, D prime. So this is 1, and this is D, and so on and so forth. We look at the midterm A prime, B, C prime. This is M2. M2 does not exist in the equation. If it does not exist, its coefficient is 0. Its coefficient is 0. So the data line D2 will be 0. This is M2 for the 3 variable D0. And so on and so forth. So we can find D0 will be 1, D1 will be D prime, D2 will be 0, D3 will be 1, D4 will be 1, D5 will be D, D6 will be 1, and D7 will be 1. A, B, C, because it is D or D prime is 1. Okay, so once we have this, we can have the answer. See, we take an A, B, C, the most significant bit to the select line S2, S1, and S0. And we have the data line 1, D prime, 0, 1, 1, D, 1, 1, as we found it. So this is by simple manipulation to the given function, okay? Just we express the function as a function of 3 variables, A, B, C, and we found the midterms M0, D0, M1, D1, up to M7, D7, then we calculated the Ds, okay? From the function easily, and this is by simple algebraic Boolean algebra manipulation. Now how about using K-map? We said the second method, we can use use 4 variable K-map to calculate the Ds. And this is very simple. So we'll have ABCD map. This is, we have, then we fill up the midterms. The midterms given to us by the function is 0, 1, 2, 6, 7, 8, 9, 11, 12, 13, 14, 15. We do this. We know the location of each midterm, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I have it for you, 13, 14, 15, 16, all of them once. So once we have this, now we will partition the map from 4 variable map to 3 variable map, and we calculate these. Now when we have a 3 variable map, we will have a map ABC, and we did not use D because the select line it's ABC. So when we have 0, 0, 0, when the select line 0, 0, 0, what we are looking for, we are looking for the map, this tiny map of 2 cells represent the data line D0, because the select line is 0, 0, 0. It means A is 0, B equal to 0, and C equal to 0. And those 2 cells, where C is equals to 0, I will have this tiny map, the tiny map, where it is 1, 1, it is the D0 map. The D0 map with the variable D. See, it is a D map. The D map, because the variable D was not taken because it's not a select line. We are working on 3 variable map. So once we have the 1, 1, we can circle it, and this will give me D0 equal to 1. D0 equal to 1. We do the same thing here. We do the same thing here. This is the map. We have ABC when it is 0, 0, 1. So this will be the map for D1. I have 0, 1. Since I have 0, 1, I cannot really simplify this. Those are the 2 pair simplified by having D0 is equal to 1, because the D will cancel out. 0 will cancel out with 1. While here, what I will have 1 here. There's no cancellation. So when I have 0, 1, what's D1 will be equal to? D1 will be equal to D prime. Why D prime? Because the DC1 and D is 0. The 1, 0 here. So this one, D1 will be equal to D prime. The same thing here. I have 0, 1, 0 will be corresponding to D2. Since both of them are zeros, D2 will be equals to 0. See, D2 is equals to 0 since both of them zeros. The same thing here. This is D3. I have 1, 1, so D3 will be equals to 1. Then D4. When I have 1, 0, 0, I will have D4. Okay, so those are the two, and D4 will be equal to 1. However, D5, I have 0, 1, and D5 will be equals to D. D5 will be equals to D because this is the 1. I have D is equals to 1. So the 0, the D is not going to cancel out because this is 0. And D6 will give me 1, and D7 will give me 1 because I have 1, 1, 1, 1. And by doing this, we really got the same answer. 1, D prime, 0, 1, 1, D, 1, 1. Okay, and this is the output F. So by using 8-to-1 multiplexer, we were able to implement the function F, okay, by using K-map. Now, how we do the 4-variable function using a 4-to-1 multiplexer? Again, we can use K-map. Method 1, we can express the function as a sum of 2 variable minterms and calculate the values. Okay, so method 2, we use a 4-variable K-map. Always, the 2 variable are the most significant bit. We are taking, they don't have to, but it is easier to do that. So we are taking the AB to the select line. So we do the same thing. See? We are taking AB, the most significant bit, to the select line as 1 and as 0. So how we do this? We do the same thing. By algebraic manipulation, we need to represent the function as a sum of M0, D0, M1, D1, M2, D2, and M3, D3, where M0 is A prime, B prime, A prime, B for M1, AB prime for M2, and AB for M3. So what's the coefficient? The coefficient will be the data lines. How we come from there to here? We will open this. We will arrange it. We did this step last time. Okay. So we get the answer here. Then we take A prime, B prime as a coefficient. We factor it out. We'll have C prime here or C prime, we have A prime B, A prime B prime, or we have C, so C prime or C D or D prime. When you factor out AB prime, we will have C prime or D prime. This is really, there are 2 steps here. 2 steps, C prime, D prime. The C prime, D prime came from, D, C prime or C, D prime. So C prime or C, D prime is C prime or D prime, Boolean algebra. So I just skipped 1 step here. The same thing with A prime B. A prime B appear here, and the coefficient is C. I don't have any A prime B now. So the coefficient will be C. AB prime, the coefficient will be C prime or CD. See, I wrote it here. So this will be C prime or D. Boolean algebra. Okay? The same, very similar to here. Okay, then we have AB, C prime or C, which is 1. And this will get me the following. D0 will be the coefficient, which is C prime or D prime, which is equal to CD prime, which is 1 NAND gate, rather than using 2 inverter and gate, and D1 will be C, and D2 will be C prime or D, okay, and D3 will be equals to 1. So once I have this, I will end up with the same answer. So you get CD, C, C prime D, C prime or D, and 1. This is the NAND gate C, NAND D, and this will be the answer. Or we can use K-map. The same thing with K-map. The select line, when we have 0, 0, this is the map for D0. When I have 0, 1, this will be clearer. When I have, this is the map for D1. When the select line, I have 1, 0, this is the map for D2. When the select line is 1, 1, giving me the map for D3. So those are the tiny map. Those map are map for two variables C and D. So when we have 1, 1, 0, 1, how we simplify it? Will get me those two will be a pair, and this one could be paired up with this one, and this will give me C or D prime. See? So those two will give me C because the 0 will cancel with the 1 for the D, so I'll get C prime. And this one will pair with this one, and the 0 will cancel with the 1 for the C, so I will get D prime. So it's a C prime or D prime. Okay, how about this map? This map all ones, so C and D will cancel out. Okay, and this will give me 1. So clearly D3 will be 1. How about D1? D1 I have only 1, 1. And this will group up. The 1 will cancel with the 0 for the D, so I get C. Okay, so I get C. So D1 is C. And we say D3 is 1 because all C and D will be cancelled out. Okay, so it is we are working on two variable map. And this map here, we can group those two. So we'll have 1, 1, 1. And for D2, this will give me D2. So those two will group up. 0 will cancel with the 1 will be C prime, or the 0 will cancel with the 1 or D. So C prime or D, very clear. So I will have C prime or D. And this will give me the 4-to-1 multiplexer inputs, the data lines, and we implemented the same function by using K-map. So any answer, any solution is a correct solution. So we have two solutions to implement the function, either by using Boolean algebraic manipulation or by using K-map. And this will be the end for this lecture. I would like to thank you so much for listening. Please subscribe. See you soon. Sincerely, Dr. Hassan. Thank you so much.